So the motivation mainly comes from what we know now as cyber physical systems. Many of you may have already heard about these things. My favorite example of a cyber physical system is actually a car. Today's modern cars, they are no longer purely mechanical systems like they used to be 20 years ago or so. Now they are actually a collection of, they also have hundreds of sensors, actuators, and processors, and they're all communicating over a shared network. Okay? And at the same time, there are millions of lines of computer code that make a car run and do what it's doing. Okay? So it is not just a computer and it's not just a purely physical system, it's a combination of the two. That is what is the main feature of such systems. You can also have cyber physical systems that are spread over a vast geographical area. You can think of something like a smart grid or something like a transportation network, and they have thousands of nodes, and you may have hierarchical and distributed topologies as a result. Okay, so if we are to give the main distinguishing feature of a cyber physical system, it is that it has a tight relationship between the physical and the cyber components. Okay, so and let's say a thumb rule to say if a system is a cyber physical system or not is to say if a software bug can cause an immediate physical damage. Okay, so such systems then pose a lot of challenges. First of all, there can be constrained resources like energy or communication and computation. So if you go back to the example of the car, we said that these hundreds of processors and sensors and actuators, they're communicating over a shared network. Or if you're talking about a distributed system like smart grid and so on, because they are distributed and spread over such huge area, the communication resources may be constrained. The sensors may be operating with low power devices, and again, energy is an issue and so on. And not only that, compared to what you may have learned in your undergrad controls or maybe even your grad controls, there we have dealt primarily with centralized control. So where all the information that is there to be known is aggregated in a central place, and then that is used to compute the control and so on. But that may not be the case any longer because things are distributed. And again, there are time critical decisions and control that needs to be done. And apart from this, there are other issues like privacy and security, which were not relevant in classical systems, are now relevant. Okay, so the gist of all this is that this requires an integrated approach to design of control and communication and computing components in many of these systems. So that is what brings us to something called network control systems. Okay, so this is an abstraction. So far I have given you some applications, and I've tried to motivate what I'm going to talk about with the help of those applications. Now this is an abstraction of how to deal with those things. So a network control system is essentially what we see in a classical control system. We have a plant, sensor, and an actuator or controller. But the distinguishing feature is that the feedback or control occurs over a communication channel or a network. So that to denote that aspect, I have just denoted it using that dotted line over there. So that poses challenges like sampling, quantization, time delays, packet drops, scheduling, unsynchronized clocks, and so on, privacy, security, and so on. Okay, so we see that network control systems are then a fundamental abstraction of cyber physical systems. So if you want to study cyber physical systems or design cyber physical systems, this is a very useful abstraction. So one of the primary questions that comes about in network control systems is when and what to communicate. So most of these questions can be boiled down to this one single question. So in network control systems, of course, that area has been there for many years. This has been there even prior to cyber physical systems became a buzzword. And there have been many threads or themes that were popular for many years. One of them is something called dynamic quantization. So in this, what happens is quantization domain itself is dynamic. So instead of having a static quantization, so no matter what the time is, certain bits will have the same meaning. that we say it's a static quantization. As opposed to that, dynamic quantization is one where the quantization domain itself is changing over time. So for example, if at time t1, if the state is represented by that blue dot over there, and okay, so I'll talk about it, so hopefully it will become clear. So that is xt1 is the state of the, it's not visible? Okay, so xt1 is the state of the system at time t1, and x hat t1 is the estimate. Somebody is keeping an estimate of the state, and it also knows that the state is within some uncertainty set S of t1. Okay, and if left untouched, meaning if left no communication is made or so on until time t2, then this uncertainty set, it grows in size. Okay, so then the idea is to quantize only that region, not the full state space or let's say a big portion of the state space. Okay, so that is the main idea of dynamic quantization, and in particular there's a phase called zoom out stage, wherein you zoom out to capture the state. Okay, to begin with, your state uncertainty set itself may not contain the planned state or the system state, so you have to zoom out to capture it and then zoom in to let's say if you want to stabilize or asymptotically stabilize it to an equilibrium point. Okay, so the advantages are that you can have much smaller packet sizes. You can in fact have asymptotic stability with finite packet sizes, which is not something that is possible with static quantization. But the disadvantages are that it requires good time synchronization between the sender and receiver and so on. Okay, so another thread that was quite popular in network control systems, and in fact it was able to show some fundamental results, fundamental limits on this, is that something called data rate limited control. So in this basically we are interested in finding what is the, if there are any fundamental limits on the rate at which feedback information must be transmitted to achieve stabilization. Okay, so and in fact there are fundamental limits, and the main idea is that the rate of data communication must at least match the rate of growth of the uncertainty of about your state. Okay, so and based on this basic idea, based on this basic idea, necessary conditions for stabilization like tasks have been found for in different settings. Okay, and often they are like very tight necessary conditions, and they are very elegant. I'll show you an example of that in the next slide. But the problem is that so far their scope is very limited. Largely they are limited to stabilization like tasks, and they are limited to one single control loop. Okay, and of course the main idea for this comes from an information theoretic perspective to controls. Okay, so just to highlight that idea, so let's consider this discrete time linear system. So this may be x is a vector here now. So then the data rate theorem says that you just look at the unstable eigenvalues of that matrix A, and then it says that the necessary average asymptotic data rate must be greater than the intrinsic rate of the rate at which uncertainty or the entropy of the system is increasing. Okay, so that is so it's very elegant, and it's in at least in this setting there are like tight sufficient conditions also. So the necessary condition is tight. Okay, so then so these are all some themes that have been quite popular, and major themes that were there in network control systems. Now I'll come to actually the main the topic that we were interested in, event triggered control. So before that, I'll just do a quick recap of this time triggered sampling. So as I said in a couple of slides ago, in network control systems we are mainly interested in the questions of when and what to communicate. Okay, so the most common paradigm for this is obviously the time triggered sampling, and usually in particular we use periodic sampling, right? So and in generally if you go to a practitioner, what they'll do is they'll just sample as fast as the hardware allows them to. That is what they do. So there is some theory for some simple settings, but it's very limited. It's limited to those simple settings. It's not very easily extendable to other settings, like where you have distributed system and so on. Okay, but also that it must be designed for the worst case scenario, and it leads to inefficiency. Okay, so you can think of that sampling. If you think of sampling itself as a decision, then that decision making is happening in an open loop fashion, because you design that sampling policy a priori, or rather the time instance at which sampling must occur, and it just happens that way. So as opposed to that, this event triggered sampling is the idea where you basically look at the data that you have currently, and you look at you know something about the system, and you know something about the control goal that needs to be achieved. So based on all these things, you can evaluate if transmission at a particular time is necessary or not. If it is not necessary, you just don't transmit. If it is necessary, then you transmit. So you can think of it as a closed loop sampling. Okay, so that is the difference. And so this idea has gained a lot of popularity in the last decade, and a lot of work has been done on this theme. And so basically, you can design efficient periodic sampling policies for a wide variety of system settings and control goals. You can have even things like distributed optimization and lots of other problems. Okay, so so just to give you a very quick example of how we may want to design an event triggered control is in this slide. So let's say our goal is to have some asymptotic stabilization of the plant state to an equilibrium point. So let's say we have a Lyapunov function, and we look at its derivative along the flow of along the trajectories of the system. And then as long as that Lyapunov function is decaying, then it's essentially going towards the equilibrium point, right? So we just don't sample as long as that is happening. So the idea is just to sample when you are about to cross that, basically when this Lyapunov function is about to increase, only then do you sample. So that is one idea if your goal is to do asymptotic stabilization of an equilibrium point. And if you had all this information, let's say you can compute this V dot if you had that information. So as I said, quite a bit of work has been done on this event triggered control. And a couple of years ago, we asked ourselves, like, what is really the case for event triggered control? So we know that it works well, but how well? So is there a quantification for it? So just to give you that idea, so this MATI is something called maximum allowable transmission interval, and that is defined for time triggered or periodic controllers. So basically, this is the max, as the full form of that acronym says, it is a maximum allowable transmission or the sampling period that is allowed. So that acts as a lower bound for the inter-transmission times for an event-triggered controller. Okay, so we know that event-triggered controller is going to transmit fewer number of times than a time-triggered controller. So we know that much. That much is guaranteed. Sorry? Yes, that is true. That is true. But we do know that that happens. Okay, so if it doesn't happen, you can impose it. Okay, so that is also possible. So then what we really care about is the distribution, or at least the average rate of transmissions, or more generally the average data rate that a particular event triggered control requires. Okay, so those blue dots are just an illustration of intertransmission times that are generated by an event triggered control policy. Okay, so if those blue stars or blue dots, they're all bunched up close to that lower bound, then it's not such a big gain. You're not gaining much, even if you're only doing slightly better than that time-triggered control. Okay, so in general, for an arbitrary event-triggered control, that's a very open question. You cannot directly address that question. So what we have addressed instead is asking ourselves, like, basically, can we design controllers with analytically quantifiable data rates? Okay, and okay, so just to give you one example, so what we have, so this is an example of a linear system that is, so x dot is equal to ax plus bu plus vt, so v is some noise, and u is a control that is based off an estimate that is maintained by the controller. So now this is a continuous time system, and we also assume that there are communication delays. So if something is transmitted at tk, it takes a while before the receiving end receives that message. Okay, it takes a delta k. So we assume that those communication delays are bounded, though they are bounded by this gamma. Okay, so we can, at each transmission time, we can also decide how many bits to send. Okay, so we can decide those transmission times as well as the packet sizes. So then on the receiving side, there is a dynamic controller which is maintaining an estimate of the state, plant state, and then it is defining a controller based on that. Okay, so then essentially at the reception times, there is a jump in the estimate. That is what is happening. And so I have just abstracted the jump map into that qk symbol, but it also depends on the time at which it is transmitted, the number of bits that were transmitted, and so on, and also the plant state, everything. Okay, so if our objective is not only to have some kind of an Lyapunov stability, but an exponential kind of stability, but if we have disturbance, we will have only, of course, practical stability. So that is what we want to achieve. So we want to have an exponential decay of the Lyapunov function, or rather an exponential bound on the exponentially decaying bound on the Lyapunov function, and that is what we want to achieve. So this can also be visualized in a different way. If you think in a state space, you can plot level sets of that function Vd, and essentially what we want to achieve is to keep the plant state within exponentially shrinking level sets of the Lyapunov function. Okay, so this we want to do under time varying rates and finite data capacity. Okay, so to begin with, let's just look at one simple necessary condition. So this is a generalization of the condition that I showed a few slides ago when I was talking about, yes?
When you're not doing event-triggered control, what is the controller applying?
When I'm not doing event-triggered control.
Between these decays, what is happening?
So yeah, so control is always being applied. Sorry. So u is equal to that k x hat. Okay, x hat itself is evolving continuously in time, but there is a jump in x hat when some new data is received. Yes, yeah. So that qk, of course, it depends on the current state, the time at which it was sent, how many bits you have sent, and all those things.
Do you make any assumptions?
No. It's just that, well, actually, we in our sufficient condition, we do choose a particular policy, and that gives a particular structure. But I've just skipped it because of to keep it short. Okay, so this necessary data rate is a generalization of the result that I presented in the discrete time case a few slides ago. So the main idea for this is that if you want to remember that this S of t, that is the state uncertainty set, no matter what the plant state is, under all such initial conditions, you still want to have asymptotic stabilization. Then what it means is that that state uncertainty set itself must belong to that exponentially shrinking Vd of t sets at all times. And that is the main idea behind getting this necessary condition. And this is just a generalization of the previous case. So here we just have the exponential decay rate also that is required in our objective. So then this is a sufficient condition. So here I am skipping a lot of details, but essentially there is in our model there is also a p bar, that is a maximum allowed packet size. And so these are some conditions that are basically saying that there's a lower bound on communication rate, so that something's nice happen. And we design an event triggering condition. Again, I'm skipping the details of it, but the main idea behind it is that we basically check if the objective can be met in the next t units of time, and that t is a function of the current time, small t, and also the planned state at that time without a transmission. So that is what we are checking. Okay, so of course, all we are doing is we are checking if it is necessary to achieve the control objective over a short time horizon. But that doesn't necessarily, just piecing these things together doesn't necessarily mean that we meet the control objective, the overall control objective asymptotically, right? But our result says that we do actually do that. We exponentially, practically, we do have exponential practical stability, and then there is no Zeno behavior. So when we are determining this sampling time instance implicitly through this event triggering condition, you can sometimes have accumulation of these events or accumulation of sampling times. So what we are saying is that that doesn't happen. Okay, so here there's a big complicated expressions, but maybe you don't have to focus there. The main idea here is that these are upper bounds on the sufficient data rates. The sufficient result that I just presented, for that there's an upper bound on the data rate. Okay, so in the case with disturbance, it looks pretty ugly. With no disturbance, it actually looks quite good. And in fact, in the scalar case, this is the same as the necessary data rate. So which means that this is a tight design that we have. Okay, in the vector case, we can actually make it tight. It's just that it requires more steps. So that is why we skipped that in the paper. Okay, so but one caveat in all of this is that both the encoder and the decoder had to know that delta k, which was the communication delay, perfectly. So that was a caveat. So this may be possible either through synchronized clocks or by sending synchronizing signals. But in general, what if that is known, if all we know is that delta k for any k is only upper bounded by that gamma, that is all we know. In that case, we have another set of results. So I'll just summarize it, the main ideas through pictures actually. So here, and I'll also explain it with the help of the scalar system. We have results for the vector case also, but I'll just explain it with that. So here the idea is, if you have that system and all you know is that your transmissions are going to take some time and that communication delay is upper bounded by gamma, then if we are using dynamic quantization, then we don't know, there is a lack of synchronization. Because you don't know when the packet was sent on the receiving side, it cannot properly decode that packet. Okay, so because of that, then we need to design how we send these packets in a different manner. And the idea is here is the idea that we were exploring is, there is implicit information in the timing of events itself. It is not just the explicit information that you send through the packets, but there is information even through the timing of the events itself. Yes. Yes, so that adds another layer of uncertainty. So yes, so here what we are saying is, in the previous case, we had this box that represented the uncertainty set about the planned state. In dynamic quantization, we quantize that essentially. But let us say if that was that ellipse in this figure, if that was the triggering set. So if at any time a transmission occurs, and you know that transmission time, then you know that to begin with, it belongs to that big box, but that it also belongs to that ellipse. So which is a smaller region that you need to quantize, that you can get away with quantizing. So that is the main idea here. And so in fact, then we have found necessary transmission rates if you did it in this manner. And so the interesting thing is that it says the necessary condition is, it says that up to a critical upper bound on the communication delay, you can get away with just finite number of bits, meaning essentially 0 transmission rate, you can stabilize the system. Okay, and as the delay grows, you need to transmit more, the rate at which you need to transmit becomes higher and higher. So these are also plots for some sufficient transmission rates. So this is just another plot. So here this rho 0 is inversely related to the packet size. Okay, so, so what this means is, these plots, what they mean is that for small bounds on delays, this gamma, small packet sizes are better. Because more frequent transmissions, they'll give you more implicit information. So you're getting that for free. Just by transmitting, you are getting some information for free, and so you just can get away with that smaller packet sizes. And for large bounds on delays, gamma, large packet sizes are better, so that you transmit fewer number of times, and you do not. So, for example, I didn't actually mention that critical gamma, beyond which actually your the timing of the events does not give you sufficient information. Okay, so beyond that critical delays, you do want to send larger and larger packet sizes. Okay, so I think I'm running out of time, so I don't know if you want me to stop here, I can stop here. Okay, so because the slides after this are on a slightly different topic, but that's okay. So far this was all in a deterministic setting, so we have also dealt with communication delays and all these things. But we also wanted to look at this problem in a stochastic setting. Here what we are dealing with is a scalar system with Bernoulli packet drops, Bernoulli IID packet drops. And here again we have a similar setup. We have a controller that maintains a state, or rather it maintains an estimate of the plant state, and it tries to control the plant based on that estimate. Here the event trigger, based on the control goal and the channel, whatever it knows about the channel, based on all those factors, it has to decide when to transmit and when not to transmit. So here I'll skip the main, or I'll skip the details, but the main idea behind the design here is that when you have IID packet drops, or basically packet drops with some probability here, so then you cannot determine the necessity of transmission on a time step based purely on the current state of the plant and so on. You also have to make an assumption of what you would do in future. That is because if you are interested in ensuring the control goal is met in an asymptotic sense, so you have to also know what you would do in future. So that formed the basis of what we designed. So what we did is that we pick a nominal family of transmission policies, which are purely time based, and then we check for one of them if basically if we can meet the control goal. So then it means that there exists a transmission policy for which I can get away with not transmitting on the current time step. So then in that case I don't transmit. So that is the idea, but I'll skip the details and I'll stop here. So I would just like to acknowledge some of my collaborators, Jorge Cortez, Massimo Franceschetti, and Mohammad Kujaste, all of them at UCSD. Okay, thank you.